Hey, welcome to The Explainer. Today we're going to dig into something really cool. It's this elegant standard that basically keeps our entire automated world from just falling apart. It's all about something called function blocks.
I mean, just picture a modern factory, right? Or even a power grid. You've got literally thousands of moving parts. Sensors, motors, controllers, you name it. And here's the kicker. They're often from tons of different manufacturers. So how in the world do you get them all to speak the same language and work together perfectly? It's a huge challenge in automation. How do you actually make that happen?
Okay, so here's our game plan. We're going to start with the factory's brain, then look at the clever idea that makes it all work. We'll check out the whole system structure, dive deep into a single block, see how they fit together, and finally, you'll see why this standard, IEC 6149, is such a big deal.
All right, let's really dig into the problem. See, back in the day, you'd have one giant central brain controlling everything. Simple enough, right? But now, things are way more advanced. The intelligence is, well, it's everywhere. It's distributed across the entire system. And that's super powerful, for sure, but man, does it create a huge headache when it comes to coordination.
So the answer isn't to write one single massive program that tries to do everything. No way! The real solution is to think differently. We need a kind of universal architecture, a standard way to, wrap up software functions into these neat, self-contained packages, little boxes of logic that you can spread out across all sorts of different hardware, that can talk to each other without any fuss, and that you can use over and over again. And that right there is exactly what the standard IEC 6199 is all about.
Okay, so how does the standard actually pull this off? Well, what's really fascinating here is that it didn't just invent something completely new out of thin air. Instead, it borrowed a really powerful idea from a totally different field: object-oriented programming.
So if you've ever done any coding, you're probably familiar with classes and objects, right? A class is just the blueprint. It defines how something should work, and an object is the actual working thing you create from that blueprint. Well, IEC 61499 takes that exact same idea and applies it to industrial automation. You have what's called a function block type. Think of that as your blueprint. And from that blueprint, you create a function block instance. That's the real, live, working component that's actually running out there on the factory floor. It's a simple concept, but it's the absolute key to making everything reusable and modular. Okay, let's get a little more specific. The function block type, or, if you want to get fancy, the Funktionsbausteintyp in German, is the master template. It's the design. It defines all the inputs, all the outputs, and the internal logic for, say, a motor controller. The beauty is you design it just once, and then you can reuse that same design absolutely everywhere you need it. And then you have the function block instance, the Funktionsbaustein instance. This is where the magic happens. This is the blueprint brought to life. It's a living, breathing copy of the type, and it has its own unique name and its own data. So you might have just one motor controller type, one blueprint, but you could have hundreds of instances of it running in your factory, where each individual instance is controlling one specific motor. All right, so we've got these building blocks, but how do you actually organize them into a huge working system? Well, the standard lays out a really clear layered structure for exactly that. The best way to think about it is like you're zooming in on a map. You start way out at the top with the entire system. That's the whole factory. Then you zoom in to a single physical device, maybe a specific controller. Zoom in again, and inside that device you'll find one or more resources. You can think of a resource as like a processor core, an independent unit of control. And then finally, running on that resource is your application. And what's the application? It's the network of all your function block instances, all wired together and doing the actual job. And really, that's the whole point of this entire structure. System, device, resource, all of it exists for just one reason: to give your function block instances a place to live and run. It's the framework that lets you take these software building blocks and logically spread them out across all the physical hardware in your factory. Okay, we've seen the big picture. Now let's zoom in all the way. Microscope level. What is actually inside one single basic function block? What are its guts? What makes it work?
So a basic block really has four main components. First, you've got event inputs and outputs. These are like signals that tell the block when to wake up and do something. Then you have data inputs and outputs, which is the actual information the block needs to work with. Inside, you have the algorithms. That's the real code, the part that does the calculations of the logic. But the true secret sauce, the conductor of the whole orchestra, is something called the Execution Control Chart, or ECC. Think of it as the block's tiny brain. It's a little state machine that just waits for an event, looks at what state it's currently in, and then decides exactly which algorithm to fire off. It's the coordinator.
Now, these basic blocks are powerful on their own, for sure, but they were never meant to be solo acts. Their real power, well, it's like Legos. A single brick is cool, but the real magic happens when you start connecting them together to build something much, much bigger. And that's where composite function blocks come into play, or zusammengesetzte Funktionsbausteine if we're sticking with the German. Now, what's really cool about a composite block is that it doesn't contain any new algorithms of its own, not a single line of new code. Instead, its entire internal logic is just a network of other function blocks, both basic and composite, all wired together. This is huge. It means you can build incredibly complex things out of simple, reusable parts that you've already tested and know work perfectly. It is modular design taken to its logical conclusion.
So, let's just step back for a second. We started with this massive, messy problem of controlling a distributed system. And now we've arrived at this really elegant, scalable solution. But what does that actually mean for people building these systems in the real world? Why should you care?
Well, the benefits are massive. First, you get interoperability. That means you can mix and match hardware from different companies, and it all just works together. You're not locked into one vendor anymore. Then there's portability. Your software isn't stuck on one piece of hardware. You can move it around. Configurability means your systems aren't rigid. You can easily update and reconfigure them as your needs change. And the big one, reusability. You can build up a whole library of these proven rock-solid function blocks. This saves an insane amount of development time and makes your final system way more reliable.
You know, the standard itself actually says it best. Its goal isn't just about writing code. It's about providing a complete architecture for the entire life cycle of an industrial system. Everything from the initial design and analysis, through configuration and implementation, all the way to day-to-day operation and maintenance. It covers the whole shebang, all in a structured, vendor-neutral way.
So, this whole component-based approach, it's really a game changer for how we build our industrial world. It's making our most complex systems stronger, more flexible, and easier to manage. And it kind of leaves you with a big question, right? If we can build entire factories and power grids using these reusable software blocks, what else could we build next?